For all of recorded human history, Betelgeuse has been one of the brightest stars in Earth's sky. Then, in late 2019, it suddenly began to disappear. Not completely, but enough for people to notice it with the naked eye. Within weeks, the star lost roughly 35% of its brightness. Observatories around the world redirected telescopes toward Orion. Astronomers began openly discussing the possibility that Betelgeuse might be approaching supernova. Then the star recovered, and nobody could fully explain why it happened. That mystery sat unresolved for years until 2025. Scientists studying Betelgeuse discovered something hidden near the star that had gone undetected for decades. A companion object orbiting so closely that it had been distorting measurements, brightness cycles, and possibly the star's behavior itself the entire time, which immediately raised a worse question. Did this hidden companion help cause the Great Dimming? And if it did, what does that mean for the future of one of the most unstable stars in the night sky? This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. It starts with one of the largest stars humanity has ever observed. Long before telescopes could resolve its surface, people noticed the color first. Not white, not blue, a deep red-orange point burning in Orion's left shoulder, steady enough to guide winter skies, but strange enough to stand apart from every nearby star around it. What we are looking at is not an ordinary star enlarged to impossible scale. Betelgeuse belongs to a category called a red supergiant, the largest class of star known to exist. These objects are so inflated that the word surface becomes misleading. The boundary between star and surrounding space begins to blur. Gas stretches outward in enormous layers, thinning gradually into darkness. Its distance from Earth is now estimated at roughly 700 light years, though astronomers argued over that number for decades. Measuring distances to unstable stars is difficult because the stars themselves move, pulse, and distort the very light we use to calculate them. Only recently did improved parallax measurements, meaning precise observations of a star's apparent motion against background stars, narrow the uncertainty range enough to give a clearer answer. Even with that refinement, Betelgeuse remains difficult to mentally hold. The star contains somewhere between 16 and 19 times the mass of our Sun, yet it shines with approximately 100,000 times more luminosity, meaning total energy output. Every second, it releases staggering quantities of radiation into surrounding space. But brightness can be deceptive. Its surface temperature is actually cooler than the Sun's. Betelgeuse averages around 3,500 Kelvin, while the Sun sits near 5,778. Cooler stars glow red. Hotter stars shift toward white and blue. That reddish color visible from Earth is effectively the temperature signature of an enormous atmosphere cooling across unimaginable distances. And despite its size, Betelgeuse is young. Astronomers estimate its age at roughly 10 million years. Smaller stars survive vastly longer because they burn fuel slowly and efficiently. Red supergiants do the opposite. They consume nuclear fuel at extraordinary rates, living fast and dying early. Betelgeuse has already exhausted the stable hydrogen burning phase known as the main sequence, the long middle period where stars spend most of their existence. Now it has entered something far less stable. Its outer layers rise and sink continuously. Vast convection cells, meaning giant circulating columns of superheated gas, churn across the star's visible face. Some may exceed the diameter of the entire orbit of Earth around the Sun. The surface brightens unevenly. It contracts slightly, then swells outward again. Material lifts away, and escapes into surrounding space. Nothing about it is calm. When you look toward Orion tonight, the red orange point at the shoulder seems quiet enough, but nearly everything that follows in this story begins there, inside that unstable glow hanging above Earth for hundreds of thousands of human lifetimes. There is a point where stars become too large to remain calm. Beyond that threshold, gravity struggles to hold the outer layers together, while radiation pressure, the outward force produced by light and heat, pushes constantly against collapse. Most stars never approach this boundary. Betelgeuse lives near it. Astronomers call the boundary the Humphreys-Davidson limit, named after the researchers Roberta Humphreys and Chris Davidson, who identified an upper stability threshold for the largest stars in the galaxy. Beyond that limit, stars become violently unstable. They shed matter so rapidly that they effectively destroy the conditions needed to keep growing larger. Betelgeuse hovers dangerously close to this edge. Its dimensions are not fixed. Over time, the star physically expands and contracts by measurable amounts, not symbolically, literally. In some observations, its radius changes by several astronomical units, a measurement equal to the average distance between Earth and the Sun. During larger expansion phases, the star could stretch beyond the orbit of Mars if placed at the center of our solar system. Then it shrinks again. This pulsing is tied partly to internal pressure fluctuations, but also to the instability of the star's outer atmosphere itself. The layers are so diffused that they behave less like a rigid sphere and more like an ocean under competing gravitational forces. Matter rises, matter cools, matter falls back inward. The entire structure breathes unevenly through space. But another detail unsettles astronomers even more. Betelgeuse rotates faster than models predict for a red supergiant of its age and size. Large stars usually slow over time as their outer layers expand. Angular momentum, meaning rotational energy distributed across a larger body, should gradually reduce surface spin. Yet Betelgeuse continues rotating at a surprisingly elevated rate. One proposed explanation reaches deep into the star's past. At some earlier point in its evolution, possibly millions or even billions of years ago, depending on orbital modeling uncertainties, Betelgeuse may have absorbed a smaller companion star. A stellar merger would transfer additional angular momentum into the larger star, effectively spinning it back up. The evidence remains indirect, but the rotation speed refuses to fit comfortably into simpler explanations, and the instability does not stop there. Betelgeuse constantly ejects material into surrounding space. Current estimates suggest it loses between 1.5 and 2 solar masses of gas and dust every million years. That outflow forms a massive surrounding nebula, meaning an extended cloud of expelled stellar matter drifting beyond the visible star itself. The cloud is uneven and distorted. Infrared imaging, which detects heat beyond visible light, reveals arcs, knots, and asymmetrical streams spreading outward in multiple directions. Some regions appear denser than others. Some seem shaped by eruptions occurring centuries apart. The structure resembles debris from repeated atmospheric upheaval rather than a smooth stellar wind. So before the hidden companion ever entered the story, Betelgeuse was already behaving like an object balanced precariously against the limits of stellar physics itself. Thousands of years before spectroscopy, orbital mechanics, or modern telescopes existed, people were already keeping track of Betelgeuse. They watched it rise season after season above deserts, coastlines, mountains, and oceans, long before anyone understood what a star actually was. Some of the earliest surviving references come from ancient Mesopotamia. Clay tablets produced by Babylonian astronomers recorded bright stars with extraordinary consistency, blending observation with mathematics in ways far ahead of their time. Betelgeuse appears among those records, making it one of the oldest continuously observed stars in human history. Its modern name traveled through several civilizations before reaching us. Arabic astronomers referred to it as Yad al-Jawaza, usually translated as the Hand of Orion. But over centuries of copying, mistranslation, and adaptation into Latin star catalogs, the original phrase slowly distorted. Letters shifted, pronunciations drifted. Eventually, the corrupted form Betelgeuse entered European astronomy and remained there. Different cultures placed the star into entirely different stories. In traditional Chinese astronomy, it belonged to the white tiger of the west, one of the four symbols dividing the sky into seasonal regions. Polynesian navigators used bright stars like Betelgeuse as orientation markers during long Pacific voyages, memorizing their seasonal positions across open ocean routes extending thousands of kilometers. And through all these interpretations, one detail remained strangely consistent. People described the star as red. Medieval Arabic sky watchers specifically noted its reddish-orange appearance in written records. That observation matters scientifically because stellar color reflects surface temperature. If Betelgeuse had changed dramatically over the last 1,000 years, those descriptions would likely differ across historical eras. Instead, the color remained recognizably stable through centuries of observation. The star was changing, but not in that way. During the 19th century, British astronomer John Herschel began documenting irregular brightness fluctuations in a more systematic form. Herschel noticed that Betelgeuse sometimes appeared visibly brighter or dimmer over long periods, suggesting the star itself was variable rather than fixed. At the time, the idea felt unsettling. Stars were widely assumed to be constant objects, reliable points anchored permanently into the heavens. Betelgeuse quietly violated that expectation, not violently, slowly, enough for attentive observers to notice patterns emerging across years. By the early 20th century, that work evolved into organized monitoring programs. In 1926, the American Association of Variable Star Observers, usually shortened to AAVISO, began maintaining continuous brightness records for Betelgeuse, using coordinated amateur and professional observations from around the world. Night after night, decade after decade, people kept measuring the same star. That archive became one of the longest uninterrupted stellar brightness datasets ever assembled. Nearly a century of observations accumulated into an extraordinary scientific baseline, allowing astronomers to compare modern behavior against generations of earlier measurements. But that long history carried an unexpected consequence. When Betelgeuse dimmed dramatically in late 2019, researchers immediately understood something was different because the records already existed. The star had fluctuated before. Everyone knew that, but not like this. Not once across nearly 100 years of continuous observations had Betelgeuse faded so deeply. If you watched Betelgeuse continuously for years, one pattern would slowly emerge from the fluctuations. The star does not brighten randomly. It breathes according to rhythm, roughly every 400 days. Its luminosity rises and falls through a repeating cycle, visible even from Earth. Sometimes the changes are subtle, sometimes more pronounced. But across decades of observation, the timing remains remarkably persistent, like the pulse of something enormous moving beneath layers of gas and light. Astronomers eventually identified the mechanism behind it. Deep inside the star, pressure waves travel through its interior plasma, meaning electrically charged gas heated to extraordinary temperatures. The physics resembles sound waves moving through air, though on scales almost impossible to imagine. Regions compress, heat builds, material expands outward, then gravity pulls everything partially back inward again. The entire star oscillates. These oscillations alter Betelgeuse's radius, temperature, and brightness together. During expansion phases, the outer atmosphere spreads and cools slightly. During contraction phases, temperatures rise again. From 700 light years away, those physical changes appear to us as a gradual dimming and brightening repeating over hundreds of days, but the rhythm was never perfectly clean. Researchers noticed another cycle, layered on top of the first one, far slower and harder to explain. Approximately every 2,100 days, or a little under 6 years, Betelgeuse passed through a second pattern of brightness variation superimposed over the shorter pulse cycle. Astronomers classified the behavior as semi-regular variability. The phrase sounds technical, but the meaning is simple. The star follows patterns that are partly predictable, yet never perfectly stable. The shorter 400-day pulse remained obvious. The longer cycle drifted more subtly through the data, sometimes strengthening the visible brightness peaks, sometimes suppressing them into unusually deep dimming periods. Together, the two cycles created interference patterns. When both cycles aligned constructively, Betelgeuse appeared brighter than expected. When the peaks and troughs opposed one another, the star dimmed more dramatically. For decades, researchers assumed the explanation remained internal. The longer cycle was interpreted as a second pulsation mode, meaning another pressure wave moving through deeper stellar layers at a different frequency. At first, the model seemed reasonable. Massive stars often support multiple oscillation patterns simultaneously. Stellar interiors are turbulent environments where temperature gradients, radiation pressure, and convection zones interact continuously. Betelgeuse already behaved strangely in other ways. A second pulse did not feel impossible, but over time the data became uncomfortable. Certain radial velocity measurements, meaning observations tracking whether the star moved slightly toward or away from Earth, failed to match predictions cleanly. Some brightness changes arrived at the wrong times. Some velocity shifts appeared too regular. The mathematics worked well enough to survive peer review, but poorly enough to leave lingering doubt. Still, the assumption remained mostly unchallenged. The 2,100-day cycle settled quietly into astronomy textbooks and long-term models, treated as part of Betelgeuse's internal behavior for years. Yet hidden inside that number was the first visible trace of something else entirely, something orbiting within the star's enormous outer atmosphere, shaping the light before anyone realized it was there. For most people, Betelgeuse had always looked permanent, even if its brightness fluctuated subtly across months or years. The changes were usually small enough to escape casual notice. Then, during the final months of 2019, the star began fading fast enough for ordinary skywatchers to see it happening with their own eyes. At first, the decline seemed merely unusual. By October, observers noticed Betelgeuse appearing weaker than expected within Orion. Through November and December, the brightness continued falling. The familiar red point no longer dominated the constellation the way it normally did. By late January of 2020, the star had dropped to roughly 40% of its typical luminosity, the faintest level ever recorded in modern observations. That immediately triggered alarm. The century-long brightness archive maintained by the American Association of Variable Star Observers showed nothing comparable anywhere in the dataset. Betelgeuse had dimmed before. Everyone knew that, but never this deeply, and never this quickly. Astronomy communities reacted almost in real time. Research groups exchanged measurements daily. Observatory alerts circulated internationally. scientific journals began publishing preliminary analyses before the event had even ended. The phrase Betelgeuse is acting strange spread simultaneously through professional astronomy networks, science news outlets, and online discussions, followed by millions of people. Because there was another possibility sitting quietly behind every conversation. Massive stars approaching supernova sometimes become unstable shortly before core collapse. Theoretical models predicted sudden eruptions, asymmetrical mass loss, and unusual brightness behavior during the final evolutionary stages preceding explosion. Several astronomers publicly acknowledged that Betelgeuse's dimming could potentially represent a pre-supernova signature. Not certainty, but plausibility. For a few months, humanity seriously entertained the possibility that one of the brightest stars in the night sky might be preparing to die within observable history. Media attention intensified rapidly. Television segments appeared worldwide. Newspapers published illustrations of daylight supernovae over modern cities. Search interest for Betelgeuse surged globally. Meanwhile, telescopes turned toward Orion. The Hubble Space Telescope redirected observation time toward the star. Infrared observatories monitored surrounding dust structures. Ground-based facilities across Europe, North America, South America, and Asia began continuous tracking programs measuring temperature shifts, spectral changes, and atmospheric disturbances in extraordinary detail. Then, unexpectedly, the fading stopped. By April of 2020, Betelgeuse had partially recovered its brightness. The worst of the dimming appeared over. Yet the recovery created a different problem. If the star truly stood on the verge of imminent supernova, why had it stabilized again? No explanation fit cleanly. One hypothesis proposed that Betelgeuse had expelled a giant cloud of dust that drifted directly between the star and Earth, temporarily obscuring the light. Another suggested an enormous cool region had formed across part of the stellar surface, reducing luminosity from within. A third possibility argued for deeper internal structural instability affecting the star's energy output itself. Each explanation matched pieces of the data. None explained everything. And buried within the unresolved inconsistencies was a detail astronomers still had not fully connected to the event: a second cycle, an unexplained periodic signal, and the possibility that Betelgeuse was not behaving alone at all. The answer emerged slowly, across years of analysis, scattered between space telescopes, infrared observatories, and spectral archives collected during the event itself. No single instrument solved the mystery alone, but eventually, the independent datasets began converging toward the same picture. Betelgeuse had not simply faded, it had erupted. Observations from the Hubble Space Telescope revealed evidence that, shortly before the dimming reached its peak, the star expelled an enormous quantity of surface material outward into surrounding space. Astronomers classified the event as a surface mass ejection, meaning a violent release of stellar gas launched directly from the outer atmosphere. The scale exceeded anything observed from the Sunday. Solar eruptions, even powerful coronal mass ejections, involve comparatively tiny amounts of matter. Betelgeuse expelled material on a vastly larger scale, enough to alter the visible appearance of the star itself across interstellar distance. But the expelled gas did not remain hot forever. As the material expanded outward from the star, it cooled rapidly. Temperature dropped below the condensation threshold for silicate compounds, meaning minerals rich in silicon and oxygen began forming microscopic dust grains inside the outflowing cloud. Infrared measurements from SOFIA, The Stratospheric Observatory for Infrared Astronomy carried aboard a modified aircraft, confirmed the presence of newly formed dust between Earth and the star. That dust blocked part of the light reaching us. The dimming, at least partially, came from obscuration rather than reduced energy production alone. A cloud had formed directly along our line of sight, effectively veiling part of Betelgeuse behind its own expelled atmosphere. But that was only half the story. At nearly the same time, imaging data revealed a large, cool region lingering across one section of the stellar surface itself. Astronomers informally called it a cold patch. Compared with surrounding regions, the area radiated less heat and therefore less visible light. The star had dimmed from underneath while simultaneously becoming partially hidden from above. Together, the two effects produced the dramatic fading observed during 2019 and early 2020. Yet one detail refused to settle comfortably. The eruption had not occurred evenly across the star. Material appeared concentrated toward a specific region rather than expelled uniformly in all directions. The geometry mattered. Betelgeuse had not merely pulsed outward symmetrically through internal instability. Something localized had destabilized one portion of the atmosphere more violently than the rest, and the consequences lingered. Following the eruption, the familiar 400-day pulsation cycle became disrupted for more than a year. The timing shifted, the amplitude changed. Rhythms that had remained relatively consistent across decades suddenly stumbled out of alignment. Astronomers noticed immediately. Stars this large are chaotic by nature, but the disturbance appeared unusually coherent, almost as though an external force had interfered with the normal oscillation patterns. Spectral measurements, meaning analyses of how different wavelengths of light changed over time, hinted that gravitational dynamics might somehow be involved. But gravity from what? The dust cloud explained the dimming. The cold patch explained the reduced luminosity. Neither explanation fully accounted for why the eruption began asymmetrically in the first place, nor why the long-term pulsation behavior became so disrupted afterward. The event had exposed a mechanism still hidden inside the system, something interacting with Betelgeuse closely enough to disturb the outer atmosphere itself. The first hints did not come from photographs. They emerged from numbers drifting slightly out of place inside astronomical datasets, subtle enough to ignore at first, persistent enough to become difficult to forget. During the 1980s, astronomers studying Betelgeuse's radial velocity measurements began noticing irregularities that repeated too consistently to feel accidental. Radial velocity refers to how quickly an object moves toward or away from Earth, measured through tiny shifts in the wavelengths of light emitted by the star itself. Stars moving toward us compress their light slightly. Stars moving away stretch it. The effect is extremely small, but measurable through spectroscopy, the analysis of starlight separated into its component wavelengths. By tracking these shifts over time, astronomers can detect motion invisible to ordinary imaging. And Betelgeuse appeared to wobble. Not dramatically. The movement was subtle, spread across years of observations. But the oscillation followed a repeating timetable that aligned suspiciously well with the longer 2,100-day brightness cycle already known from photometric monitoring, meaning repeated measurements of the star's luminosity. That coincidence attracted attention. When an unseen object orbits a star, gravity causes both bodies to move around a shared center of mass. The larger star appears to shift slightly back and forth through space. This method later became one of the primary techniques used to discover exoplanets around distant stars. The mathematics looked familiar. Several research papers across the following decades proposed the possibility that Betelgeuse might possess a hidden companion orbiting within its outer atmosphere. The idea explained the repeating radial velocity pattern naturally. It also offered a possible explanation for why the longer brightness cycle behaved with such unusual regularity compared with ordinary stellar pulsations. But there was a problem. Actually detecting a companion near Betelgeuse bordered on impossible using conventional techniques. The star is overwhelmingly luminous. Any smaller object orbiting nearby would be drowned inside the glare, effectively erased by surrounding radiation before telescopes could isolate it cleanly. The scale difference mattered enormously. Trying to image a faint companion beside Betelgeuse resembled attempting to identify a candle positioned directly beside an industrial floodlight from thousands of kilometers away. Even advanced observatories struggled to separate the light sources spatially because the star itself occupied such an enormous apparent size in the sky, and many standard binary detection methods failed outright. Transit measurements, where orbiting objects pass visibly in front of stars, become unreliable when the star's atmosphere lacks a sharply defined edge. Precision imaging also suffers because Betelgeuse constantly changes shape, brightness, and atmospheric structure over time. The object under observation refused to remain stable long enough for clean interpretation. So, the companion hypothesis occupied an uncomfortable middle ground for years, plausible enough to survive serious discussion, weak enough to avoid consensus. Researchers debated whether the repeating signals reflected external gravity or merely complex internal pulsation patterns not yet fully understood. Some favored orbital explanations. Others argued that red supergiants naturally produce chaotic variability, difficult to model precisely. Science remained cautious. Suspicion alone could not confirm a second star. Without direct observational evidence, the hypothesis stayed officially unproven, no matter how persuasive the patterns appeared. Yet the unexplained periodicity continued resurfacing across independent datasets, waiting for an instrument capable of separating something almost completely hidden inside the light of Betelgeuse itself. The breakthrough arrived not through a giant new space observatory, but through precision, patience, and an instrument designed to outmaneuver Earth's atmosphere one fraction of a second at a time. On December 9th, 2024, astronomers, using the Gemini North Telescope atop Mauna Kea in Hawaii, captured the first direct observational evidence that Betelgeuse possessed a close orbiting companion. After decades of suspicion, the hidden source disturbing the star's behavior finally left a measurable signature strong enough to survive scrutiny. The instrument responsible was called Alapeke, the Hawaiian word for fox. Alopeak specializes in a technique known as speckle interferometry. Under normal conditions, atmospheric turbulence smears starlight into blurry distortions before telescopes can record clean detail. Speckle interferometry avoids that problem by taking thousands of extremely short exposures in rapid succession, effectively freezing the atmospheric distortion moment by moment. Computers then reconstruct the signal. By combining those exposures mathematically, astronomers can recover spatial details far sharper than conventional ground-based imaging normally allows. The method works especially well for detecting faint structures buried inside the glare of brighter objects, and Betelgeuse required exactly that kind of precision. The companion signal was extraordinarily weak compared with the surrounding stellar light. Researchers estimated the object to be roughly 6 magnitudes fainter than Betelgeuse, meaning it emitted approximately 250 times less visible light. Under ordinary observing conditions, the companion disappeared completely inside the overwhelming luminosity of the red supergiant. But this time, something remained visible inside the reconstructed data. Not a clean photograph, not a sharply separated second star. The detection instead appeared as a measurable atmospheric and gravitational signature embedded within the structure of the light itself. The companion revealed its presence indirectly, through distortion patterns and orbital influence rather than through conventional imaging. Still, the implication was unmistakable. Andrea Dupree of the Harvard Center for Astrophysics led the observing team, continuing work she had already become known for during the detailed analysis of the Great Dimming. Her group approached the results cautiously. Extraordinary claims in astronomy demand extraordinary verification, especially when overturning decades of uncertainty surrounding one of the most studied stars in the sky. So the data underwent months of analysis. Additional observations were compared against orbital models. Independent researchers reviewed the reconstruction methods. Statistical noise, instrumental artifacts, and atmospheric contamination all had to be ruled out carefully before any announcement could survive peer review. Only then did the discovery become public. In July of 2025, the confirmation was formally announced to the astronomical community. The repeating radial velocity patterns, the strange long-term cycle, the asymmetrical disturbances in Betelgeuse's atmosphere suddenly reorganized into a coherent explanation. The object had been there the entire time. A few months later, in September of 2025, the International Astronomical Union officially approved a name for the companion. Siwarha, derived from Arabic and often translated as her bracelet, echoed the linguistic ancestry already embedded inside the name Betelgeuse itself. After nearly half a century of suspicion, the conclusion finally became unavoidable. Betelgeuse was not alone. For decades, astronomers searched for something large enough to disturb Betelgeuse, yet faint enough to remain hidden beside one of the brightest stars in Earth's sky. The answer, when it finally emerged, turned out to be surprisingly ordinary by stellar standards. Siwarha is not another giant. Current estimates place its mass between roughly 1.4 and 1.6 times that of our Sun, making it a relatively modest star compared with the enormous red supergiant it orbits. In another region of the galaxy, observed independently, Siwarha would likely appear unremarkable, just another stable star quietly burning hydrogen inside its core. But location changes everything. Researchers believe Siwarha is probably a blue-white main sequence star. Main sequence refers to the long, stable phase where stars fuse hydrogen into helium inside their cores, steadily producing energy through nuclear fusion. Our Sun currently occupies this stage. Siwarha does too, though at a somewhat hotter and more luminous level. Yet, despite being larger and hotter than the Sun, Siwarha remained invisible for most of human history. Betelgeuse overwhelms it completely. The red supergiant radiates so intensely across such an enormous atmospheric volume that nearby light sources vanish inside the surrounding glare. Even advanced telescopes struggle to isolate anything orbiting close enough to interact directly with the star's extended outer layers. And close is exactly where Siwarha lives. Evidence suggests the two stars formed together approximately 10 million years ago from the same collapsing molecular cloud, meaning a giant region of cold gas and dust drifting through interstellar space. They are not strangers temporarily captured by gravity. They are siblings, born from the same material during the same stellar formation event. But time affected them differently. Betelgeuse, far more massive, evolved rapidly into instability while Siwarha remained comparatively young and stable. Massive stars burn fuel at extreme rates, smaller stars conserve it. So while Betelgeuse expanded into a swollen red supergiant approaching the end of its life, Siwarha remained compact and orderly, still orbiting nearby. Its orbital period now appears to be approximately 2,170 days, almost perfectly matching the mysterious long cycle hidden inside Betelgeuse's brightness variations for decades. That agreement changed everything about how astronomers interpreted the system. The cycle was never merely pulsation, it was orbital motion. Every 2,170 days, Siwarha completes another path around Betelgeuse, producing the repeating radial velocity shifts and periodic brightness changes that researchers once attributed solely to internal stellar oscillations. The signal hidden inside the data belonged to gravity all along, and the orbit itself is extraordinarily tight. Betelgeuse possesses no sharply defined surface. Its outer atmosphere extends outward through enormous diffuse layers of gas, gradually fading into surrounding space. Siwarha moves directly through those layers during its orbit, effectively traveling inside the outskirts of another star's atmosphere. That interaction is not gentle. Gas compresses around the companion. Material becomes disturbed and accelerated. Gravity pulls asymmetrically across Betelgeuse's outer regions, while radiation and stellar wind stream continuously between the two bodies. The system behaves less like two isolated stars orbiting peacefully and more like an ongoing atmospheric collision unfolding across millions of kilometers. Imagine moving a fast vessel through dense ocean water at night. The ship itself may disappear into darkness, but behind it, the disturbed water remains visible for long distances, tracing the object's path through waves, turbulence, and displaced current. Something similar happens inside the atmosphere of Betelgeuse. Siwarha does not orbit through empty space surrounding the red supergiant. It travels directly through the star's outer atmospheric layers, regions so extended and diffuse that they blur gradually into surrounding interstellar gas. The companion moves through that material continuously, compressing and disturbing it as gravity and orbital motion interact together. And behind Siwarha, a wake forms. Astronomers describe it as a dense spiral trail of compressed gas and dust extending outward from the companion's orbital path. Material becomes heated, accelerated, and redistributed as the smaller star pushes through Betelgeuse's atmosphere. The effect resembles hydrodynamics, meaning the physics governing fluid motion, except the fluid in this case is stellar plasma spread across millions of kilometers. The wake is not static. It rotates with the orbit itself, circling Betelgeuse every 2,170 days alongside Siwara's motion. As the structure sweeps around the star, different regions pass between Earth and the luminous surface beneath. That changes the light reaching us. The disturbed gas inside the wake absorbs and scatters radiation differently than surrounding undisturbed material. Spectroscopy revealed this indirectly through unusual absorption signatures embedded inside Betelgeuse's spectrum, meaning specific wavelengths appeared weakened in patterns consistent with dense orbiting gas structures. Researchers were not seeing Siwarha directly. They were seeing what Siwarha did to the atmosphere around it. The analogy used repeatedly by the Discovery team compared the phenomenon to a boat wake crossing water. But scale transforms the comparison into something almost surreal. The boat is itself a star somewhat larger than the Sunday. The water is the extended atmosphere of a red supergiant so vast it could engulf planetary orbits. And the entire interaction unfolds while both objects move through space at orbital velocities impossible in ordinary human experience. Yet the mathematics matched beautifully. Every 2,170 days, the wake completed another orbit and returned to roughly the same geometric alignment relative to Earth. The mysterious long-term dimming cycle that astronomers once interpreted as deep internal pulsation suddenly acquired a far more coherent explanation. The cycle was environmental. Betelgeuse was being externally modulated by another object moving through its atmosphere, periodically altering how light escaped from the system. What observers had called variability now appeared partly observational, shaped by changing gas geometry between the star and us. That realization changed the meaning of decades of data. Betelgeuse still pulsates internally. The star remains unstable, turbulent, and physically dynamic in its own right. But some portion of the famous irregular behavior, the long dimming cycle, the asymmetrical atmospheric disturbances, even certain spectral anomalies, now traced back to a companion humanity did not know existed. The star had not been acting alone. For generations, astronomers believed they were studying the isolated behavior of a single red supergiant approaching the end of its life. In reality, they had been watching a binary interaction unfold the entire time, hidden inside the light itself. After Siwarha's existence became difficult to dispute, astronomers returned to the Great Dimming with an entirely different framework in mind. Data that once seemed disconnected suddenly began aligning into patterns that had not been obvious before. Timing became the first clue. When researchers reconstructed Siwarha's orbital position during late 2019, they found that the companion occupied a very specific region relative to Betelgeuse and Earth during the dimming event. The geometry placed Siwarha near a point where its gravitational influence on the red supergiant's outer atmosphere would have been unusually concentrated along one side of the star. That mattered enormously. Gravity does not need to overpower a star completely to destabilize it. Tidal forces, meaning differential gravitational pulling across extended structures, can stretch and disturb material unevenly. On Earth, the moon produces ocean tides through this mechanism. Around Betelgeuse, the scale becomes vastly larger and far more violent. One leading interpretation now suggests that Siwarha may have amplified conditions already developing inside the star. Betelgeuse was unstable long before the Great Dimming occurred. Its atmosphere remained turbulent, convective, and asymmetrical across multiple layers. Pressure waves moved continuously through the stellar interior. Material rose and fell unpredictably. The star was already primed for disturbance, but unstable systems often require triggers. As Siwarha passed through a critical orbital position, its gravitational pull may have intensified stress within a localized atmospheric region, helping initiate or strengthen the enormous surface mass ejection observed shortly afterward. The companion did not necessarily create the instability itself. Instead, it may have acted upon a structure already near failure, like pressure against weakened rock or a spark near dry fuel. Researchers increasingly describe the event as an interaction between internal and external forces rather than a purely spontaneous stellar eruption. Betelgeuse provided the volatile environment. Siwarha may have supplied the final disturbance needed to tip one region into collapse and mass expulsion. That interpretation remains actively debated. Scientific papers continue testing competing models against observational data collected during and after the dimming. Some astronomers argue that Betelgeuse's internal convection patterns alone remain sufficient to explain the eruption. Others believe the orbital correlation with Siwarha is now too strong to dismiss as coincidence. But the companion framework currently explains more pieces simultaneously than earlier models did. It accounts for the asymmetry of the ejection. It matches the timing of the long orbital cycle. It offers a mechanism for localized atmospheric destabilization. And it helps explain why the dimming disrupted the familiar pulsation behavior so dramatically afterward. Most importantly, it changes how astronomers think about the event itself. The Great Dimming may not have been random. If Siwarha's orbit contributed directly to the eruption, then similar alignments could produce related disturbances again when the companion returns to comparable orbital positions. The cycle becomes not merely historical, but predictive, and that possibility has transformed future observation planning. Roughly 2,170 days after the original event, Siwarha will once again approach the same orbital geometry relative to Betelgeuse. Telescopes across multiple wavelengths are already preparing to monitor the system closely during those periods, searching for atmospheric disruptions, dust formation, spectral changes, and signs that the interaction between the two stars is beginning to intensify again. Right now, as Earth moves quietly through another year around the Sun, Siwarha is hidden behind Betelgeuse from our perspective. The companion sits on the far side of the red supergiant relative to Earth, buried completely inside the overwhelming glare and atmospheric distortion surrounding the larger star. For the moment, it is effectively invisible again. But orbital mechanics are predictable. Once astronomers reconstructed Siwarha's path with enough precision, they could calculate when the companion would emerge back into a more favorable viewing geometry. Current models place that reappearance window sometime during 2027, and researchers are preparing for it already. Among stellar astronomers, the coming alignment is being treated as one of the most important scheduled observation opportunities of the decade. Unlike unpredictable transient events, this one can be anticipated years in advance. Telescope schedules, observation campaigns, and coordinated international monitoring programs are already being assembled around the expected orbital position, because the next opportunity may reveal far more than the first detection did. The original discovery confirmed Siwarha existed. The upcoming window could begin characterizing the system in extraordinary detail. Multiple observatories are expected to participate simultaneously, combining optical, infrared, and spectroscopic measurements across different wavelengths of light. The Hubble Space Telescope remains involved. Ground-based interferometers, meaning systems that combine light from multiple telescopes to simulate a much larger instrument, are also expected to contribute. Facilities in Chile, Hawaii, and Europe are preparing observation strategies specifically designed to isolate faint atmospheric structures near Betelgeuse's outer layers. But much of the anticipation centers around the James Webb Space Telescope. Webb operates primarily in infrared wavelengths, allowing it to detect heat signatures hidden behind visible light obscuration. Researchers hope its sensitivity may finally resolve portions of the interaction zone between Siwarha and Betelgeuse directly, particularly the compressed wake structures and dust flows moving through the outer atmosphere. If successful, the observations could transform current models completely. Astronomers want more precise measurements of Siwarha's mass, surface temperature, luminosity, and chemical composition. They also hope to map the density and geometry of the wake trailing behind the companion, tracing how gas behaves under continuous gravitational disturbance inside a red supergiant atmosphere. Another question matters just as much. Can Siwarha's tidal influence be measured in real time? If the companion genuinely alters Betelgeuse's atmospheric behavior during specific orbital phases, astronomers may be able to observe those disturbances directly as they develop. Tiny shifts in spectral lines, localized changes in atmospheric velocity, or asymmetrical heating patterns could reveal the mechanics of the interaction unfolding live across millions of kilometers. This is no longer ordinary follow up work. The data collected during 2027 could force revisions to how scientists model mass loss in giant stars approaching supernova. Current theories often treat red supergiants as largely isolated systems. Betelgeuse now suggests that close companions may fundamentally reshape how these stars evolve, erupt, and eventually die. For the first time in recorded history, humanity is preparing to observe a red supergiant and its hidden companion interacting together with instruments capable of watching the process unfold almost as it happens. For years, one of the most common questions surrounding Betelgeuse sounded deceptively simple. When will it explode? The honest answer was always uncomfortable. Before Siwarha entered the picture, estimates for Betelgeuse's eventual supernova ranged from roughly 10,000 years to more than 100,000 years into the future. That uncertainty existed because astronomers could not fully separate which behaviors reflected deep internal instability and which represented temporary surface phenomena. The star seemed chaotic. Brightness fluctuations, atmospheric disturbances, irregular pulsations, and asymmetrical eruptions all suggested a red supergiant approaching the violent final stages of stellar evolution. Some models interpreted those observations as evidence that Betelgeuse might already be entering advanced instability preceding core collapse. But the discovery of Siwarha forced researchers to recalculate many of those assumptions. Once the 2,170-day cycle was identified as orbital rather than purely pulsational, a significant fraction of Betelgeuse's apparent irregularity suddenly acquired an external explanation. Some of the variability previously attributed to deteriorating internal structure now appeared connected to gravitational interaction with the companion. That distinction matters enormously for stellar evolution models. A star approaching imminent supernova generally shows escalating internal instability tied directly to fusion processes deep inside the core. But if part of the observed instability actually originates from atmospheric disturbance caused by an orbiting companion, then the underlying stellar interior may be somewhat calmer than researchers originally believed. Current modeling, therefore, leans toward longer timelines. Many astronomers now suspect Betelgeuse may remain stable for at least 100,000 years, possibly longer, before true core collapse occurs. The star is still nearing the end of its life by cosmic standards. But near in astronomy rarely means imminent on human timescales. And yet, Siwarha complicates the picture in another direction at the same time. As the companion moves through Betelgeuse's outer atmosphere, it continuously disturbs and strips material away from the red supergiant. Gas becomes compressed, accelerated, and redistributed through tidal interaction and wake formation. Over thousands of years, that process may significantly increase the total mass loss rate of the system. Mass loss changes everything for giant stars. The rate at which a red supergiant sheds outer material strongly affects how pressure, temperature, and fusion balance evolve inside the core. Lose enough mass, and the structure of the star changes dramatically. Internal layers shift. Nuclear burning stages accelerate or slow in response. So Siwarha both stabilizes and destabilizes the interpretation simultaneously. It explains away some signs of apparent internal crisis while potentially increasing long-term atmospheric erosion around the star itself. Researchers are still trying to quantify which effect dominates over tens of thousands of years. That uncertainty is why scientific caution remains important here. No serious astronomer currently believes Betelgeuse is likely to explode within any timeframe relevant to modern civilization. The star is unstable, yes, violent, certainly, but supernova prediction remains extraordinarily difficult, even with nearby stars. Still, one conclusion now appears unavoidable. Whenever Betelgeuse eventually dies, it will not behave like an isolated red supergiant collapsing alone in empty space. Siwarha's gravity, orbital motion, and surrounding wake structures will shape the geometry of the explosion itself, influencing how material escapes into the surrounding galaxy long after the star is gone. One night, without warning, Orion's familiar shoulder would ignite brighter than anything humanity has ever seen in the night sky apart from the sun and possibly the moon. The change would not unfold gradually across generations. It would happen within hours. Betelgeuse would die as a Type 2 core collapse supernova. That phrase describes the final destruction of a massive star whose core can no longer support itself against gravity. Deep inside Betelgeuse, nuclear fusion would eventually stop producing enough outward pressure to balance the immense weight pressing inward from the surrounding layers. The core would collapse catastrophically in seconds. Then the explosion would begin. From roughly 700 light years away, the supernova would appear extraordinarily bright from Earth. Estimates vary depending on the final explosion energy and the structure of the surrounding atmosphere, but most models suggest it could rival or even exceed the brightness of the full moon at peak intensity. You would see it during daytime. At night, it would cast visible shadows across landscapes. Ancient historical supernovae observed within our galaxy already demonstrated this effect at far greater distances. Betelgeuse would be significantly closer than most previously recorded naked-eye supernovae in human history, and the brightness would not vanish immediately. For weeks, possibly months, the explosion would dominate the sky, while the expanding debris cloud radiated heat and light outward through surrounding space. Gradually, the luminosity would begin declining as the ejected material cooled and spread across larger distances. The star itself would be gone. What remained at the center would depend on Betelgeuse's final mass at the moment of collapse. One possibility is a neutron star, an object only about the size of a city, yet containing more mass than the Sun, compressed into matter so dense that atomic structure partially collapses under gravity. The other possibility is darker. If enough mass survives the explosion and falls inward after collapse, the core may continue compressing until it forms a black hole instead. The threshold separating neutron star formation from black hole formation remains uncertain, especially in systems as complicated as Betelgeuse and Siwarha. But either outcome would leave behind expanding wreckage visible for thousands of years. The supernova remnant, meaning the outward moving shell of gas, dust, and heavy elements ejected during the explosion, would continue glowing long after the initial event faded from naked eye visibility. Future civilizations, using instruments not yet invented, would still study the expanding debris cloud across centuries and millennia. Earth itself would remain safe. At 700 light years, the radiation reaching our planet would disperse too broadly to threaten the atmosphere or biosphere significantly. Current estimates suggest supernovae become seriously dangerous only within roughly 25 to 50 light years, depending on explosion, geometry, and gamma ray emission. Betelgeuse lies far beyond that threshold, so the event would arrive not as catastrophe, but as spectacle, a nearby stellar death visible across the entire planet. Children born during the brightest weeks would grow up hearing stories about nights bright enough for people to walk outdoors without artificial light. But afterward, the winter sky would carry an absence humanity has never experienced before. Orion would still rise above Earth. The belt would remain. Rigel would remain. But the left shoulder, the red point humans have watched since before recorded civilization, would be gone forever. When Betelgeuse finally dies, humanity will not first learn about it through telescopes. No astronomer will look up and suddenly notice a new light in Orion before everyone else. The first warning will arrive invisibly, deep underground and beneath Antarctic ice, carried by particles passing through Earth almost without resistance. Hours before the explosion becomes visible, detectors on our planet will already know. At the instant Betelgeuse's core collapses, conditions inside the star will become unimaginably extreme. Temperatures will surge into billions of degrees. Matter will compress violently inward. Atomic structure itself will begin breaking apart under gravitational pressure. And then the neutrinos will escape. Neutrinos are subatomic particles produced during nuclear reactions and stellar collapse. They possess almost no mass and interact so weakly with ordinary matter that trillions pass through your body every second without leaving any trace at all. Most continue through entire planets untouched. Inside a collapsing red supergiant, however, neutrino production becomes catastrophic in scale. During the first moments of core collapse, the dying star releases an enormous burst containing more neutrinos than the Sun will emit across its entire lifetime. Those particles leave immediately. Visible light cannot. Even after the core collapses, the outward moving shock wave still requires hours to fight through Betelgeuse's immense outer layers before the explosion reaches the surface and becomes visible from Earth. The neutrinos race ahead at nearly the speed of light, while photons, meaning particles of visible light, remain trapped temporarily inside the expanding stellar debris. So the neutrino burst reaches us first, and humanity already has instruments waiting for it. Deep beneath Mount Ikano in Japan sits Super Kamiokande, one of the most sensitive neutrino detectors ever constructed. The facility contains roughly 50,000 tons of ultra-pure water enclosed inside a massive underground chamber lined with thousands of light sensors. Normally, the detector remains almost silent. But if Betelgeuse collapses, neutrinos passing through the water would occasionally strike atomic nuclei, producing tiny flashes of light detectable by the surrounding instruments. Thousands of interactions could occur within a single second. At nearly the same moment, another detector would trigger at the opposite end of the planet. The Ice Cube Neutrino Observatory at the South Pole embeds optical sensors throughout a cubic kilometer of Antarctic ice, transforming part of the glacier itself into a particle detector. IceCube continuously monitors for high-energy neutrino events arriving from deep space. A Betelgeuse collapse would overwhelm both systems simultaneously, and they are connected to automated alert networks. Astronomers maintain coordinated warning protocols specifically for nearby supernovae. If detectors register the characteristic neutrino burst pattern associated with stellar core collapse, alerts would spread globally within minutes. Telescopes across Earth and in orbit would immediately pivot toward Orion before any visible explosion appeared in the sky. There are rehearsals for this. Observatories have response procedures already established, including data sharing systems, emergency scheduling protocols, and coordinated observation campaigns designed for the exact moment the neutrino alarm activates. So one day, somewhere on Earth, scientists monitoring quiet underground detectors may suddenly watch their instruments erupt with signals from a star 700 light years away, announcing that Betelgeuse has already begun to die, while Orion still appears unchanged overhead. Long before astronomers understood Betelgeuse's present behavior, the star had already been leaving records of its past, drifting quietly through surrounding space. Those records are made of gas and dust. Every eruption, every unstable pulse, every century of atmospheric loss has carried material outward from the star into the surrounding interstellar medium. Unlike planets or solid worlds, red supergiants continuously shed parts of themselves as they evolve. Betelgeuse has been doing this for thousands of years, and the expelled material does not disappear evenly. Using infrared telescopes and spectroscopic analysis, astronomers can examine the structures surrounding the star and reconstruct portions of its history. The process resembles archaeology more than traditional astronomy. Researchers are not merely observing what Betelgeuse is doing now. They are studying fossilized evidence of events that happened centuries or millennia ago. Closest to the star, multiple distinct shells of ejected material remain visible. These shells represent separate episodes of mass loss occurring at different times. Some appear relatively dense and sharply defined, while others have already spread outward into thinner structures. By measuring expansion speeds and distances from the star, astronomers can estimate when specific eruptions occurred. The timing stretches across thousands of years. But the geometry of the shells became even more interesting after Siwarha entered the story. Several of the surrounding structures are noticeably asymmetrical. Material appears thicker or more extended along particular directions rather than expanding outward in smooth spherical patterns. That irregularity now carries new meaning. Researchers suspect Siwarha's orbital position during earlier eruption events may have influenced how the expelled gas moved through space. Gravitational interaction between the two stars could have redirected material unevenly, shaping the density and trajectory of each shell as it expanded away from Betelgeuse. The companion may therefore be embedded inside the archaeological record itself. Farther from the star, the structures become more diffuse and ancient. These outer regions likely formed during an earlier stage of Betelgeuse's evolution, before it expanded into its current red supergiant phase. Evidence suggests the star once existed as a hotter blue supergiant, radiating more intensely at shorter wavelengths before swelling outward dramatically. That transition may have happened only around 40,000 years ago. In stellar terms, that is recent. Infrared observations have also revealed something stranger beyond the main nebula, an enormous arc-shaped structure extending far ahead of Betelgeuse's direction of motion through the galaxy. Researchers believe this feature may be a bow shock, meaning compressed gas formed as the star's stellar wind collides with interstellar material while moving rapidly through space. The effect resembles the curved wave forming ahead of a moving ship, so the environment surrounding Betelgeuse is shaped simultaneously by eruption, history, orbital interaction, atmospheric loss, and galactic motion. The result is not a simple cloud surrounding a single star, but a layered and evolving structure carrying traces of multiple physical processes unfolding across different eras. And every year, the picture grows more detailed. The dust surrounding Betelgeuse is not random debris. It is memory preserved in matter, recording ancient eruptions, orbital disturbances, and evolutionary transitions, long before humanity, possessed instruments capable of understanding what those structures meant. For most stars in the universe, distance reduces everything to points of light. Even through powerful telescopes, stars usually remain unresolved, tiny, luminous dots without visible shape or texture. Betelgeuse is different. It is one of the very few stars beyond our Sun whose surface humanity has managed to observe directly as an actual disk. Not perfectly sharp, not photographically detailed in the ordinary sense, but large enough in apparent size for modern interferometry to reveal structure across its face. And what we found looks nothing like a stable world. The most detailed observations came from the Very Large Telescope Interferometer in Chile, often shortened to VLTI. Interferometry works by combining light from multiple telescopes spread across large distances, effectively creating the resolving power of a much larger instrument. The resulting images revealed an irregular surface, mottled with bright and dark regions. Nothing about it appeared smooth. The bright areas correspond to enormous convection cells, rising columns of superheated plasma transporting energy outward from deeper layers inside the star. On the Sun, convection creates granules roughly the size of continents. On Betelgeuse, a single convection cell may exceed the width of Earth's entire orbit around the Sunday. The scale becomes difficult to process. These structures do not remain fixed for long. Over periods of months, the visible surface changes continuously as hot material rises, cools, and sinks again. Regions observed during one observing campaign may vanish completely by the next, replaced by new disturbances erupting from below. The star behaves more like weather than geology. Temperature across the visible surface varies dramatically as well. Some regions glow hotter and brighter, while others cool into darker patches. These differences produce the uneven appearance visible in interferometric maps, giving Betelgeuse a shifting mottled texture, unlike the sharply defined surfaces people often imagine when thinking about stars. One of those darkened regions became historically important later. Before astronomers fully understood the Great Dimming, interferometric observations had already captured an unusually cool surface patch associated with the event. At the time, researchers recognized the anomaly, but did not yet understand its role in the dramatic brightness collapse that followed. The evidence existed before the interpretation did. But perhaps the strangest aspect of Betelgeuse is that its surface is not truly a surface at all. There is no solid crust, no sharp atmospheric edge, no clear boundary where star ends and empty space begins. Density simply decreases gradually outward. The visible atmosphere thins across enormous distances until it fades into surrounding interstellar gas almost imperceptibly. Siwarha itself orbits within this transition region, moving through material that technically still belongs to Betelgeuse while simultaneously existing in open space. That distinction becomes meaningless here. The outer atmosphere stretches across hundreds of millions of kilometers, forming a diffuse region more like a continent-sized fog than a conventional stellar surface. Radiation, plasma, magnetic activity, dust formation, and orbital interaction all overlap inside this enormous, unstable volume. So when astronomers speak about the surface of Betelgeuse, they are describing something fundamentally unfamiliar, a star whose visible structure shifts continuously, whose atmosphere dissolves gradually into space, and whose outer layers are large enough for another star to travel through them. Astronomy has spent centuries classifying stars as isolated objects, individual furnaces suspended alone inside surrounding darkness. But over the last few decades, that picture has been changing steadily. Massive stars rarely live alone. Current research increasingly suggests that most large stars form inside binary or multiple systems, meaning two or more stars orbiting a shared gravitational center. In fact, truly solitary massive stars may be less common than astronomers once believed. Betelgeuse now sits directly inside that shift in understanding. Before Siwarha's confirmation, Betelgeuse was already among the most intensively studied stars in the sky. Researchers monitored its brightness, mapped its atmosphere, measured its motion, analyzed its chemistry, and tracked its variability across generations of increasingly advanced instruments. And still, the companion remained hidden. That realization has unsettled many astronomers because it raises a broader and more uncomfortable possibility. If a companion star could remain undetected beside one of the closest and most famous red supergiants in existence, then how many other stellar systems are currently being misunderstood for the same reason? The question extends far beyond Betelgeuse itself. Binary interaction is now recognized as one of the dominant forces shaping stellar evolution. Stars exchanging matter, distorting each other gravitationally, altering orbital momentum, and triggering asymmetrical eruptions behave very differently from isolated stars evolving alone. Gravity changes everything. Mass transfer between companions can accelerate stellar aging, alter chemical composition, spin stars up to abnormal rotational speeds, or even trigger explosive instability. In close systems, tidal forces reshape atmospheres continuously, redistributing gas and affecting how stars lose material over time. Betelgeuse may now represent one of the clearest nearby examples of that process unfolding visibly. Researchers are already revising models of red supergiant evolution to account for hidden companions more carefully. Earlier estimates of atmospheric instability, pulsation behavior, and mass loss rates may have systematically overlooked external gravitational effects embedded inside long-term observational data. And the implications keep spreading outward. Several other nearby red supergiants have already been flagged for renewed examination following the Siwarha discovery. Astronomers are revisiting decades of variability measurements, searching specifically for repeating orbital signatures hidden beneath behavior previously interpreted as purely internal stellar pulsation. Patterns once dismissed as noise now appear potentially significant. The detection technique itself also attracted enormous attention. Speckle interferometry, using the Alopique instrument, succeeded where many traditional approaches failed because it could isolate subtle structures buried inside overwhelming stellar glare. Researchers are now discussing whether similar surveys should target additional giant stars systematically. The goal is no longer merely studying Betelgeuse. The goal is determining how incomplete the broader picture may be. Because Siwarha changed more than the interpretation of one famous star, it demonstrated that even modern astronomy, equipped with space telescopes, interferometers, and decades of accumulated data, you can still overlook major components of nearby stellar systems, hiding inside difficult observations. Betelgeuse taught astronomers something profound about itself, but it also exposed a limitation in how humanity has been interpreting massive stars altogether, reminding us that some of the universe's most important influences remain invisible until technology, patience, and timing finally align closely enough to reveal them. Deep inside Betelgeuse, beneath the turbulent atmosphere and the drifting clouds surrounding the star, matter is being transformed continuously into new forms that did not exist before the star was born. This process is called nucleosynthesis. The word simply means the creation of atomic nuclei through nuclear fusion, the mechanism powering stars across the universe. Under immense pressure and temperature, lighter elements combine into heavier ones, releasing enormous amounts of energy in the process. Inside Betelgeuse, that process has advanced far beyond the stage our Sun currently occupies. The star no longer fuses hydrogen quietly inside a single central core. Instead, fusion now occurs in layered shells surrounding increasingly hotter inner regions. Hydrogen continues burning into helium farther outward, while deeper layers fuse helium into carbon and oxygen. Closer to the center, the reactions become more extreme. Current models suggest Betelgeuse is likely fusing carbon and neon in some of its innermost regions, stages reached only by the most massive stars nearing the ends of their lives. Each new reaction requires higher temperatures and produces heavier elements than the one before it. The interior resembles an onion built from nuclear fire. Layer upon layer of fusion zones surround the collapsing core, each producing different elements under different physical conditions. Carbon accumulates, oxygen accumulates, neon, magnesium, and silicon continue building deeper inside the star as gravity steadily compresses the interior toward higher densities. And every reaction pushes Betelgeuse closer to collapse. Fusion can continue producing energy efficiently only up to iron. Once iron begins accumulating in sufficient quantity, the process stops generating outward pressure. At that point, gravity inevitably wins. The core falls inward. The supernova begins. But before that happens, the star is manufacturing enormous quantities of future matter. When Betelgeuse finally explodes, those elements will not remain trapped inside the collapsing star. The supernova will scatter them outward across dozens of light years, mixing freshly forged atoms into surrounding molecular clouds and interstellar dust. That chemistry becomes the raw material for future systems. Over immense spans of time, portions of the ejected material may condense into new stars, rocky planets, icy moons, atmospheres, oceans, and eventually biological systems capable of observing the universe around them. This is not poetic metaphor. The calcium inside human bones, the oxygen carried through human blood, the magnesium inside living cells, the silicon inside planetary crusts, all originated inside earlier generations of stars that lived and died long before the solar system existed. Stellar death created planetary chemistry. Betelgeuse is participating in that same process right now. The star is not simply approaching destruction. It is manufacturing the heavy elements required for future worlds while slowly exhausting the conditions, allowing those reactions to continue. And the scale of that production is staggering. Across millions of years, Betelgeuse has converted enormous quantities of hydrogen into progressively heavier matter through nuclear fusion operating continuously at temperatures and pressures almost impossible to visualize. The star functions less like a glowing object suspended in space and more like a colossal chemical engine reshaping atomic structure itself. A factory powered by gravity. And somewhere deep inside that unstable interior tonight, new atoms are still being made. Everything we have discussed about Betelgeuse carries a hidden complication built directly into the structure of the universe itself. Every image, every spectrum, every eruption, every fluctuation we observe from Earth arrives late. Very late. Betelgeuse sits approximately 700 light-years away, meaning the light entering your eyes tonight began its journey toward Earth around the year 1325. While medieval kingdoms rose and collapsed on Earth, those photons were still crossing interstellar space. We never see Betelgeuse in the present. The great dimming observed during 2019 was not truly happening in 2019 at all. The event itself unfolded around the early 14th century, while humanity remained unaware of it for 700 years. The same applies to the companion detection announced in 2025. The orbital interaction recorded by astronomers reflects conditions inside the system during the Middle Ages. The star we study is historical, and that creates an unavoidable implication that many people find deeply unsettling once they fully absorb it. Betelgeuse may already be gone. The supernova may already have happened. If the star exploded 100 years ago, by Earth's calendar, around 1926, the light from that event would still remain centuries away from reaching us. Humanity would continue observing an apparently intact Betelgeuse until roughly the 27th century before learning what had already occurred. Even an explosion happening tonight would remain invisible to Earth for another 699 years. There is currently no method capable of bypassing that delay. Information cannot travel faster than light. The universe imposes that limit, absolutely. Every observation we make beyond the solar system therefore becomes an observation of the past rather than the present moment. Astronomy is time travel through observation, and not metaphorically. When you look toward Orion, you are literally seeing ancient light arriving now after centuries of travel through interstellar space. The star overhead is not a live broadcast. It is a delayed message transmitted long before modern civilization existed. That changes the meaning of now. Human intuition assumes the night sky exists simultaneously with us, that distant stars occupy the same shared present we experience on Earth. But the cosmos does not operate that way. Every visible object occupies a different historical layer depending on distance. The moon appears roughly 1 second old. Sunlight is about 8 minutes old. The nearest stars appear years old. Galaxies visible through deep telescopes may appear millions or billions of years in the past. Some no longer exist in the forms we currently observe. Their light simply continues traveling toward us across immense distances. Betelgeuse occupies a strange middle ground in that scale, distant enough for centuries of delay, close enough for human history to remain relevant to the comparison. The photons reaching Earth tonight departed the star, while handwritten manuscripts preserved knowledge by candlelight across medieval Europe and Asia. And somewhere beyond those arriving photons, hidden farther ahead along the path we cannot yet see, the future state of Betelgeuse already exists. Whether the star still burns, whether Siwarha still orbits it, whether the supernova has already begun, the universe knows already. We simply have not received the message yet. Every human who has ever looked carefully at the winter sky has seen the same pattern waiting there. 3 stars across the belt, bright Rigel below, Betelgeuse glowing softly at the left shoulder, red against the surrounding cold white stars. Empires changed beneath it. Languages disappeared beneath it. Entire civilizations rose, mapped the heavens, told stories about Orion, and vanished while that same red point remained fixed above them night after night. Across all of recorded human history, the constellation has appeared essentially unchanged to the naked eye. That permanence is an illusion. When Betelgeuse eventually explodes, the transformation will begin with brilliance. For weeks or months, the supernova will dominate the sky with extraordinary intensity, temporarily becoming more striking than the star humanity knew before. But the brightness will fade. The expanding remnant will continue dispersing outward through space, while the visible point itself weakens year after year. Eventually, the naked eye star will disappear entirely, not dimmed into obscurity but absent altogether. Orion will survive. The belt stars will remain aligned above Earth during winter nights. Rigel will still shine blue-white near the lower corner of the constellation. Bellatrix will remain visible. The overall structure will still resemble the familiar hunter traced across human mythology. But the balance will feel wrong. For billions of people across thousands of years, Betelgeuse has anchored that pattern visually and culturally. Ancient navigators used it. Agricultural calendars referenced it. Oral traditions from widely separated cultures independently incorporated the same bright shoulder into their interpretations of the sky. No human being has ever seen Orion without it. Every surviving depiction of the constellation across recorded history includes that red star. Ancient cave art, Mesopotamian tablets, Polynesian navigation traditions, medieval astronomical charts, modern star atlases, all preserve essentially the same arrangement. The future disappearance of Betelgeuse therefore represents something historically unprecedented. It may become the first major visible alteration to a familiar naked eye constellation pattern observed directly by technological civilization. Humanity has recorded eclipses, comets, novae, and planetary motions for thousands of years, but the permanent removal of a first magnitude star from one of the sky's most recognizable shapes belongs to a different category entirely. And yet, on cosmic timescales, nothing unusual is happening. Stars are born, stars evolve, stars die. The night sky has always been changing gradually as stellar motions reshape constellations across hundreds of thousands of years. Human lifetimes are simply too short to perceive most of those transitions directly, but this one will happen fast enough to notice. That changes the emotional scale of the event completely. The sky overhead carries continuity deeper than almost anything else in human experience. People separated by centuries, languages, religions, and continents still shared the same visible Orion rising above them each winter. That shared reference point matters more than we often realize. So, when Betelgeuse eventually disappears, the loss will not feel catastrophic in the ordinary sense. Earth will remain safe. The galaxy will continue evolving. Future stars will form from the debris eventually. But something ancient and continuous will quietly end. Not an apocalypse, something softer than that. A familiar shape finally becoming unfamiliar. Long before the explosion becomes visible from Earth, the space around Betelgeuse will already be changing violently. The instant the star's core collapses, an enormous shock wave will begin racing outward through layers of stellar material that took millions of years to accumulate. In only seconds, Betelgeuse will release more energy than our Sun can generate across its entire 10 billion year lifespan. Matter will not drift away gently. It will erupt outward at thousands of kilometers per second, carrying newly forged elements into the surrounding darkness with extraordinary force. The expanding debris field will collide first with the complex environment already surrounding the star, the shells of gas and dust expelled during countless earlier eruptions. Those ancient layers are still there. Some lie relatively close to the star, dense and uneven from recent mass ejections. Others drift much farther out, diffuse and stretched by time. When the supernova shockwave strikes them, the collisions will compress and heat the material until entire regions begin glowing intensely across visible and infrared wavelengths. The surrounding nebula will ignite piece by piece. Astronomers call this ionization, the process where atoms become electrically charged after violent heating strips electrons away. The effect will transform invisible gas into an immense luminous structure expanding through interstellar space. And inside that expanding catastrophe, Siwarha will still be orbiting. For a brief period, the smaller companion star may find itself engulfed within the outer layers of supernova ejecta. Whether it survives unchanged depends on several uncertain variables: the exact explosion energy, the final mass of Betelgeuse before collapse, and the geometry of Siwarha's orbit at that moment. One possibility is dramatic. If Betelgeuse suddenly loses enough mass during the explosion, the gravitational balance holding the binary system together could collapse entirely. Siwarha would then break free, launched outward as a runaway star moving independently through the Milky Way for millions of years. But another future remains possible. If the collapsing core forms a neutron star, an ultra-dense stellar remnant containing more mass than the Sun compressed into a city-sized sphere, Siwarha may continue orbiting it. The system would survive in altered form, transformed from a red supergiant binary into something far stranger. Such binaries matter enormously in astrophysics. Over long timescales, neutron star systems can generate intense X-ray emissions, gravitational disturbances, and in some cases even mergers powerful enough to ripple spacetime itself. The explosion will also produce gamma rays, extremely energetic electromagnetic radiation traveling outward at light speed. Earth lies far beyond the dangerous range, but space observatories will detect the burst immediately. Instruments already orbiting our planet are designed specifically to monitor such events continuously. And then the long study will begin. A nearby supernova of this scale would become one of the most examined astronomical events in human history. Future generations of scientists will analyze its expanding remnant for centuries, tracing the chemistry, dynamics, and geometry of the explosion in extraordinary detail. Because nearby supernovae are rare, most humans will never witness one. But eventually, somewhere in Earth's distant future, Orion's familiar shoulder will detonate into light, and the surrounding galaxy will carry the consequences outward for thousands of years afterward. Most supernovae in our galaxy happen unseen. Some erupt deep inside dense clouds of interstellar dust where visible light never escapes. Others occur on the far side of the Milky Way, so distant that even powerful explosions fade into the crowded background of stars. Astronomers estimate that the Milky Way experiences roughly one or two supernovae every century, yet most humans never notice a single one. The galaxy keeps exploding quietly. The last supernova, clearly visible to the naked eye from Earth, occurred in 1604, when Johannes Kepler documented a brilliant new star appearing in the constellation Ophiuchus. For weeks, it rivaled the brightest objects in the sky before gradually fading away. No comparable event has appeared in our galaxy since. There was another famous explosion in 1987. SN 1987, A erupted inside the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, approximately 168,000 light-years away. Even across that enormous distance, the explosion became visible without telescopes. Modern detectors captured neutrinos from the event for the first time in human history, confirming theoretical models of stellar collapse that had existed for decades. But Betelgeuse is vastly closer. At approximately 700 light-years away, its eventual supernova would become the nearest stellar explosion observed with modern scientific instruments by an extraordinary margin. The difference in proximity changes everything. A supernova that distant remains an astronomical event. A supernova this close becomes an environment. Every major observatory on Earth would turn toward it simultaneously. Optical telescopes would monitor the changing brightness hour by hour across multiple wavelengths. Radio observatories would trace the expanding debris cloud. Infrared instruments would map heated dust structures forming around the blast. Gamma ray detectors would record high energy radiation almost instantly. And beyond ordinary light, entirely different systems would activate. Neutrino detectors buried underground would capture the first particles escaping the collapsing core. Gravitational wave observatories would search for minute distortions in spacetime itself, ripples generated by asymmetries inside the explosion. Humanity has never observed a nearby supernova with this level of technological reach before. The scientific return would be enormous. Inside the Milky Way, there are between 200 billion and 400 billion stars, yet only a tiny fraction are red supergiants approaching core collapse. Betelgeuse belongs to that rare category, one of perhaps only a few hundred scattered across the galaxy, and it is the closest one we know intimately. We have mapped its surface, measured its pulsations, watched its eruptions, tracked the hidden orbit of its companion. No other supernova candidate has been studied with comparable detail before death. That matters because supernovae shape galaxies. Every explosion enriches surrounding space with heavier elements forged inside stellar cores. Carbon, oxygen, silicon, calcium, iron, all of it spreads outward into the interstellar medium after collapse. Over millions of years, those enriched clouds condense again into new stars, new planetary systems, and eventually new chemistry capable of supporting life. The Milky Way exists in its current form partly because earlier stars exploded before ours was born. Betelgeuse is simply the next chapter in that ongoing cycle. Somewhere within 700 light years of Betelgeuse, there are other skies. The region surrounding the star contains thousands of stellar systems scattered through the Orion arm of the Milky Way. Many possess planets. Some almost certainly contain rocky worlds orbiting within stable temperature ranges where liquid water could exist. From those worlds, Betelgeuse would not appear distant or obscure. In some skies, it might dominate entire constellations, burning as an enormous red, variable star brighter than almost anything nearby. On planets orbiting stars relatively close to Orion, Betelgeuse could cast a faint color across the night landscape during peak brightness periods. And eventually, from those same worlds, the explosion will arrive. But not at the same moment. One of the strangest consequences of cosmic distance is that simultaneity, the idea that events happen universally at one shared time, begins to dissolve once light years separate observers. The universe does not provide a single synchronized present stretching across space. Each location carries its own version of now. This is not philosophy, it is physics. Special relativity, developed by Albert Einstein in 1905, demonstrated mathematically that time and simultaneity depend on the observer's position and motion through spacetime. So when Betelgeuse finally collapses, different regions of the galaxy will encounter that event at radically different moments. A civilization living 100 light years closer to Betelgeuse than Earth would witness the supernova a full century before humanity. Another located several thousand light years farther away might not see it until long after human civilization itself has disappeared. Every observer will believe they are witnessing the event in real time. And in a local sense, they will be correct. The explosion itself may last only seconds at the core, followed by weeks or months of visible brightness. Yet the information carried by that event will expand outward through the galaxy as an ever-growing sphere of light, neutrinos, radiation, and particles traveling at near light speed. The sphere will never stop expanding. Year after year, century after century, the signal will continue crossing interstellar space. Long after Earth's continents have shifted and Orion itself has distorted through stellar motion, the light from Betelgeuse's death will still be traveling outward toward distant systems. Some of those systems do not even exist yet. New stars will form before the wavefront reaches certain regions of the galaxy. Entire planetary systems may emerge from collapsing molecular clouds, while the expanding light from the supernova continues silently approaching across thousands of years. The scale becomes difficult to hold together mentally. An event shorter than a human breath will project consequences across 100,000 light years of galactic space and over timescales longer than recorded civilization itself. Briefness and permanence coexist simultaneously in astronomy with very little regard for human intuition. But perhaps that is what makes the universe feel so strange at night. When you look toward Orion, you are not looking at a single shared moment suspended above Earth. You are looking into a layered field of different histories arriving together at your eyes from different depths of space. And somewhere out there, from another world under another sky, someone else may already have seen Betelgeuse disappear. Siwarha survives almost every version of this story. Even while Betelgeuse dominates attention with its size, instability, and eventual destruction, the smaller companion star carries a timeline stretching vastly farther into the future. A star with roughly 1.5 times the Sun's mass can continue burning hydrogen for billions of years, remaining stable long after Betelgeuse itself has vanished into remnant debris. But Siwarha is not ordinary anymore. For millions of years, it has orbited inside the outer atmosphere of a red supergiant, moving through turbulent gas dense enough to shape its evolution directly. Stellar wind from Betelgeuse has continuously streamed past it, carrying ionized particles, magnetic disturbances, and expelled material across enormous distances. Some of that material may have accumulated onto Siwarha itself. Astronomers call this accretion, the gradual gathering of surrounding matter through gravity. Over long enough timescales, accretion can subtly alter a star's outer chemistry, rotation rate, and magnetic behavior. Siwarha therefore may no longer resemble a pristine main sequence star formed in isolation. It has spent its entire life beside a stellar catastrophe in progress. Radiation from Betelgeuse alone would shape the environment dramatically. The red supergiant emits roughly 100,000 times more luminosity than the Sun, flooding nearby space with heat and energetic particles. Siwarha has evolved inside that environment since birth. Then the explosion arrives. If the binary system survives the supernova intact, Siwarha will suddenly find itself orbiting something radically different. In place of an immense red supergiant, there may remain a neutron star, the collapsed core of Betelgeuse compressed into a sphere barely larger than a city. The physics of neutron stars barely resemble ordinary matter. A single teaspoon of neutron star material would weigh billions of tons on Earth. Surface gravity becomes so intense that atoms themselves distort under pressure. Some neutron stars rotate hundreds of times each second while emitting narrow beams of radiation from their magnetic poles. If Siwarha remains gravitationally bound to such an object, the pair would become one of the strangest binaries in the galaxy, and the system would continue evolving. Over billions of years, Siwarha itself will gradually exhaust the hydrogen fuel sustaining nuclear fusion in its core. The star will swell outward, expanding into a red giant phase much smaller than Betelgeuse but still enormous compared to its earlier state. At that stage, Matter from Siwarha may begin falling toward the neutron star. This process can become extraordinarily violent. Material spiraling inward forms a rapidly rotating accretion disk, heated to immense temperatures through friction and gravity. Such systems can emit powerful X rays visible across enormous interstellar distances. Under certain conditions, the neutron star may begin spinning faster again as incoming matter transfers angular momentum into it. Astronomers call these rejuvenated objects millisecond pulsars, neutron stars rotating with astonishing speed while emitting regular pulses of radiation across space. So the end of Betelgeuse may only mark the midpoint of Siwarha's existence. The companion that remained hidden for most of human history could continue evolving through multiple exotic phases, long after Orion itself changes shape in Earth's sky. The system grows stranger the farther forward you follow it, and the timeline ahead still stretches billions of years beyond that. 700 light years sounds manageable when spoken aloud. The phrase fits comfortably inside a sentence. Your mind hears the number, compares it loosely against other large distances, and moves forward. But the reality behind it refuses to compress into anything truly familiar. Human intuition breaks long before that scale begins. If you boarded a commercial aircraft and somehow traveled continuously toward Betelgeuse at ordinary cruising speed, the journey would take roughly 800 million years. That span exceeds the time separating the Cambrian explosion from modern civilization. Entire branches of life on Earth evolved, flourished, and vanished across shorter intervals. And still, you would not arrive. Even light itself requires 7 centuries to cross the distance. The photons entering your eyes tonight left Betelgeuse during the early 14th century, before the Black Death spread across Europe, before telescopes existed, before most modern nations formed. You are always seeing the past. The scale problem becomes stranger when distance combines with size. If Betelgeuse replaced our Sun at the center of the solar system, its outer atmosphere would stretch beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, and the asteroid belt would all exist inside the star itself. 300 million Earths could fit within its volume. And yet, within the Milky Way, Betelgeuse is considered nearby. Our galaxy spans approximately 100,000 light-years from side to side. Relative to that scale, 700 light-years barely registers as local separation. Astronomers casually call it a neighbor, but the Milky Way itself shrinks almost to irrelevance against the observable universe, which extends roughly 93 billion light-years across. Hundreds of billions of galaxies occupy that volume, each containing hundreds of billions of stars. At that scale, the entire Milky Way compresses into something too small for meaningful analogy. Language begins failing there. Human consciousness evolved to navigate forests, coastlines, weather, seasons, and social groups. Our intuitions were shaped by meters, kilometers, years, and lifetimes. We instinctively understand falling objects, walking distance, hunger, aging, and daylight. Astronomy does not operate within those scales. The distances are too large for direct sensory comprehension, while the timescales exceed biological memory completely. You can understand the mathematics intellectually while still failing to feel the reality underneath it. But perhaps that mismatch matters, because when you look toward Betelgeuse, you are confronting a universe fundamentally indifferent to human proportion. The star is incomprehensibly huge compared to Earth, yet insignificant beside a galaxy, which itself disappears almost entirely inside the wider cosmos. And so do we. A species living briefly on one planet around one ordinary star, somehow learned to measure objects hundreds of light years away, reconstruct their histories, detect hidden companions orbiting inside stellar atmospheres, and predict explosions that may not occur for 100,000 years. That contradiction sits at the center of astronomy. We are tiny creatures with minds too small for the universe, attempting to understand it anyway, and somehow, little by little, succeeding. Before astronomy became science, it was pattern recognition under darkness. People stepped outside, looked upward, and noticed that certain lights returned, season after season, with extraordinary consistency. Constellations shifted across the year, predictably enough to guide planting cycles, migration routes, ceremonies, and navigation across open oceans. The patterns were real. Stars rose and set, planets wandered, eclipses repeated, comets appeared unexpectedly and vanished again. Human beings learned the rhythms long before they understood the mechanisms beneath them. Meaning came afterward. Cultures layered stories onto the sky because stories made enormous distances feel survivable and familiar. Orion became a hunter. Betelgeuse became a shoulder, a hand, a marker of winter, a signal embedded inside mythology and memory simultaneously. None of that was irrational. It was one way of relating to the universe before mathematics, spectroscopy, or telescopes existed. The observations themselves were often astonishingly careful. Ancient astronomers tracked planetary motions with remarkable precision, using nothing but patient attention across generations. Betelgeuse accumulated identities over time. It became a navigation reference for sailors crossing open water beneath dark skies. It became an agricultural signal tied to changing seasons. Later, it became a scientific anomaly, then a variable star, then a red supergiant nearing collapse. And now it has become something stranger still, a binary system shaped partly by an invisible companion orbiting inside its outer atmosphere. Each layer altered the meaning without erasing the earlier ones. Modern astronomy often strips away mythology, but what replaces it is not emptiness. The scientific version of Betelgeuse is arguably far more disorienting than the mythological one. A star large enough to engulf planetary orbits, fluctuating unpredictably, shedding enormous shells of matter, orbited by a hidden stellar companion, preparing eventually for catastrophic collapse. Reality became stranger than symbolism. But scientific understanding also changes the experience of looking upward in subtler ways. Once you know the light from Betelgeuse began traveling toward Earth during the Middle Ages, the star stops feeling immediate. Once you know Siwarha remained hidden beside it for all of recorded history, every earlier observation acquires a second unseen layer. The companion was always there. Every ancient skywatcher saw the effects without recognizing the source. Every sailor navigating by Orion looked toward a binary interaction system already shaping itself through gravity and stellar wind. Even the dimming patterns recorded across decades contained information humanity could not yet decode. The universe had not changed. Only the interpretation changed once better tools arrived. That distinction matters because discovery does not create truth. It rearranges our relationship to truths that already existed independently of us. Siwarha orbited Betelgeuse for millions of years before any human being suspected it. And still, somehow, a species of short-lived primates on one planet eventually detected it. That may be the strangest part of astronomy altogether. You are made from atoms forged inside ancient stars, living briefly beneath a sky filled with objects too large and distant for intuition to grasp fully. Yet your mind remains capable of extracting meaning from faint arriving light across centuries of travel. We look upward, we notice patterns, and slowly, generation by generation, the universe becomes legible enough to feel even more mysterious than before. Some future generation will inherit the moment accidentally. There will be no warning visible to ordinary eyes at first. One winter evening, someone will step outside beneath Orion and notice a brightness that does not belong there. A white point burning where a familiar red star once stood, brighter than Venus, bright enough to cast pale shadows across the ground. At first, it may look impossible, but the light will intensify over days. News will spread globally within hours. Telescopes will turn automatically. Spectrographs will begin dissecting the explosion wavelength by wavelength, while neutrino detectors compare timestamps from the first arriving particles. Humanity will watch together. For weeks, Betelgeuse's death will dominate the night sky. The constellation will appear wounded, almost unbalanced, with a temporary beacon replacing the familiar red shoulder carried across all of recorded history. Then the fading will begin. The expanding debris cloud will cool gradually as it spreads outward through space, its brightness decreasing month after month. Hydrogen emission lines will weaken. Shock fronts will move into older shells of expelled gas. Radio observatories will track the remnant growing larger each year. And eventually, to the unaided eye, the brilliance will disappear. Orion will still rise over Earth during winter evenings. The belt stars will still cut across the darkness in their familiar line. Rigel will still burn blue-white near the hunter's foot. But the left shoulder will no longer glow. There will simply be absence there. Inside that absence, matter will continue moving outward at thousands of kilometers per second. Iron forged in Betelgeuse's core will drift into interstellar space beside nickel, silicon, oxygen, calcium, and carbon assembled slowly across millions of years of fusion. Nothing will be wasted. The expanding remnant will merge gradually into the surrounding medium of the galaxy, enriching cold molecular clouds that future stars and planets may eventually condense from. Some fraction of that material will enter worlds not yet formed. Some tiny fraction may someday become living tissue again. But the original star will not return. Siwarha, if it survives intact, will continue through the galaxy carrying the aftermath physically written into its orbit and atmosphere. Future astronomers may study it for thousands of years, reconstructing the explosion from the surviving companion's altered motion and composition. Near the center of the nebula, a neutron star may remain, an object barely wider than a city, dense enough that a spoonful of its matter would outweigh mountains, rotating silently in darkness, emitting pulses of radiation across empty space while the debris cloud expands around it, century after century. And beyond all of this, the Milky Way will continue almost unchanged. New protostars are already assembling inside cold dust clouds tonight. Older stars are dying elsewhere unseen, behind curtains of gas near the galactic core. Black holes continue orbiting invisibly through the stellar disk. Spiral arms continue rotating over spans longer than civilizations survive. The universe does not commemorate endings. It transforms them into beginnings quietly, continuously, without pause. Late at night, after enough time spent with this star, the story begins to feel less like astronomy and more like perspective. For over a century, Betelgeuse sat in one of the most recognizable places in the sky, while quietly refusing to behave the way astronomers expected. Its brightness shifted, its atmosphere pulsed unpredictably, its outer layers erupted asymmetrically into surrounding space. Data accumulated year after year, precise but incomplete. The inconsistencies remained, not because scientists lacked intelligence or care, but because part of the system was hidden. Siwarha was buried inside the glare of a star so luminous that ordinary methods simply could not separate one object from the other. The evidence existed only indirectly, scattered through subtle orbital signatures and unexplained cycles, waiting for instruments sensitive enough to uncover them. And eventually, they did. A new observational technique arrived. Thousands of rapid exposures were combined through speckle interferometry, a method designed to reconstruct clarity from atmospheric distortion. Out of that noise emerged structure. Out of structure emerged confirmation, a companion star orbiting there the entire time. Suddenly, decades of confusing measurements reorganized themselves. The long brightness cycle made sense. The strange wake patterns made sense. Even the great dimming acquired a new framework. Betelgeuse did not become simpler once the mystery was solved. It became deeper. The hidden mechanism only revealed a larger level of complexity underneath. This is how science often moves forward. Not through certainty arriving cleanly all at once, but through long stretches of ambiguity, interrupted by brief moments where understanding shifts shape. Old observations remain true, but their meaning changes completely when placed into a different structure. And all of this happened across a gulf of approximately 700 light years. The photons entering your eyes tonight began traveling toward Earth during the 14th century, long before modern telescopes, long before electricity, long before anyone understood that stars were nuclear furnaces assembling heavier elements inside their cores. Yet here we are, a species that evolved beside rivers and forests, somehow learned to measure stellar spectra, detect neutrinos underground, calculate orbital dynamics, and identify a hidden companion moving through the atmosphere of a dying supergiant hundreds of light years away. The scale mismatch is astonishing. Betelgeuse has existed for roughly 10 million years. Human civilization occupies only a tiny fraction of that span. The star will likely survive for tens of thousands of years more before collapsing into supernova. Everyone alive tonight will vanish long before that final explosion reshapes Orion forever. But for one brief interval, our species became aware of it. That awareness matters. Because the universe is not arranged for human understanding, it does not simplify itself to match the scale of a human life or mind. The distances remain enormous. The timescales remain overwhelming. The stars continue evolving whether anyone watches or not. And still, we look up. Still, we build instruments. Still, we ask questions across impossible distances. Still, somewhere tonight, beneath Orion, someone will notice that quiet red star and realize they are looking at something ancient, unstable, alive with hidden motion, and carrying the chemistry of future worlds inside itself even now.